So just to reiterate, 50% more content, 50% more questions, about a third on the first half material, first half of the class. There'll be all multiple choice. For the first half material, there'll be no code you have to write, so you don't have to remember how to write the code. But you need to remember which syscalls are which. And these are the topics from the first half. And then the second half will be about 2/3 of the exam. And we'll have all the topics we covered on compilers and tool chains. Questions on material or stuff that I should cover or that you'd like me to cover? Let me also announce office hours. So I merely extended the dates of the office hours. At least I thought I did. I didn't extend the dates. I didn't extend the dates. I thought I extended the dates. Let me extend these. So the way this is going to work is my office hours will go to, what's the date today? The 21st. So my office hours will go to the 28th. I'll just have the same office hours, Monday and Wednesday, same place, same time. So there'll be office hours today. There'll be office hours this Wednesday. That's the 23rd. And then there will be office hours again the 28th. And that'll be the day that everything is due. All the project stuff is due on the 28th. So that'll be like one last chance to talk about your exam, talk about projects, and then all the projects will be due that night. I should have all exam grades out by then as well, so you can come and talk about your exam. And then, by the 29th, my plan is to have all grades regraded and in. So, then you'll have grades by then. That's my plan. Things don't always work out that way, but yeah. Cogen what? Oh, sorry about that. Yeah, so I was delayed on this. Thank you to my grader for reminding me. I just finished grading them. I'll upload the grades after this today. They are finished grading, and I'll upload it today so you'll be able to see that and do your resubmissions for that. And as I said, I'm going to try to grade. I know this is Cogen 3 is due here, but I'll try to grade it earlier. I think Friday is my target to grade it, maybe Thursday. But I'll grade it this week, so that way you'll have a chance to see a new grade. And you won't get a point off because the due date on here is 4/28. So there is no late submission for Cogen 3, but I'll try to grade it early so you have feedback. Other questions on end of semester stuff, logistics? So these are the office hours. They're just going to continue to be Monday, Wednesday, and Monday. Let me know on EdStem, or let me know if you have other issues in between then, or you can't make it, or you need to go virtual. Let me know, but the last one on Monday will probably be longer than an hour. I'm guessing there'll be more people coming, so I'll just stay longer. All right, let me go over the logistics of the exam just to remind you. We're going to use UCF here, and I think I'm also going to have the graders and the TAs check you off when you leave. So you're going to show your ID, and they're going to check you off. I think we lost track of some people who may have left early. But otherwise, it'll be the same. Excluding those who are in SAS, you'll take the exam in SAS. But those who are coming to the room, you need to be in the exam room physically. It's going to be on web courses, but you need to be in the exam room physically. And we're going to check that with web courses and also check your ID to make sure you're physically present. And you should submit your exam on time before you leave the room. So you can show the grader or TA, show your ID, leave the room, and then, you'll use your UCF ID. So make sure you have your UCF ID or a picture of it. People sometimes use driver's license, something with your name, so we can make sure that it's you. As before, I'll bring some limited number of physical exams in case you need a physical exam. But you can take it on a web-enabled device where you can, you can take it on a tablet if you want. You can take it on a computer as long as that's the only thing visible on your screen. Make sure you bring paper notes. Don't put the notes on your machine. Bring paper notes. I know it's going to be nearly impossible to do, but I'll have people sort of allocated throughout the room, one seat apart, and then fill in the space when people come in. And so yeah, when you're taking the test, and we'll have people looking around. I hate doing this, but there are people who like cheat and keep their phone out and stuff like that. So just have your notes, physical notes, not digital notes, physical notes. If you want scratch paper, bring your own scratch paper if you like. And the exam. So that's either going to be the laptop with only the exam, or the physical questions and a writing implement. And no other information sources, no encoding answers on the pencil or other tricks like this. So no other information besides this. So for SAS, I've put in the updated start date. So hopefully that will work out. I haven't set the exam yet, but that'll be on paper because last time there was issues with web courses. So the SAS exam will just be on paper. So they'll print it out for you, and we'll do it on paper. Questions on logistics? So very similar to last time, with the minor change about checking the ID when you leave. Any other questions on the final? All right, hopefully that's all clear. I guess I'll just go over the content. Maybe let's start with the second half material, second half material better. Let's start with the second half material. So some of these I took from basically from the project, homework, and lecture notes, and I'll go through. And I do have the exam. I think basically finalized the questions, so I'll use those as well to give you some hints on what to know and what not to know, what not to have to be on the exam. All right. But before we begin, let's go over the content of the exam. And let's start with the second half material. Let's start here with source to processes. All right, remember this is the overall tool chain. So which part of the tool chain takes the machine code of your executable and puts it into memory and starts it running? Any takers? What actually takes, the loader. The loader takes the executable instructions, puts it in memory, branches to the starting point of your program, and starts running. That's the loader. Which translates C code or simple IR to assembly? Which step translates programming language to assembly? Yeah, the compiler. And what does the linker do? What's the linker do? Yeah.
I think she kills Gannon or something.
That's link. That's link.
It takes all the object files and puts them together into one program.
That's right. Just as brave as link. So it takes all the object files, but importantly, it also makes it one executable, and importantly, it resolves all of the undefined functions. So if you have functions defined in one object file, and they're called by a different object file, the object file that just calls them will not have that code for that function. So the linker matches up callees and callers. What about the assembler? What's the assembler do? Any video game references for assembly? Yeah. Yeah, go ahead. Yeah, translates or assembles assembly language into machine code. So different from compilation because assembly is closer to a one-to-one set of instructions. It's not really arguably not a different language or not a structured language. Preprocessor, I'm not going to ask about the preprocessor. The preprocessor includes macros and if-defs. All right, that's all of them. Questions on the tool chain? So I won't ask you, the commands to run. You should know GCC, but GCC runs almost all of these for you. Which one of these does GCC not run for you? Which one of these? So it's all but one that GCC will run for you. The loader, yeah, the loader. The loader is part of the kernel, part of the operating system. That's the exec syscall. Behind the exec syscall is the implementation of the loader. But the rest of these GCC actually calls for you, runs for you. All right, questions on toolchain, source to process? Everybody good on that? Okay. Let's go over compiler basics. What does this code do? Just take a second to look at this code, and the answer is like on the screen, but what does this code do, and why? Yeah.
Basically getting two numbers and operator and doing the addition on those, but it's really like looking as a interpreter.
Yeah. Interpreter is the key word. So it's taking in ASCII code, which has no mathematical meaning. They're just symbols. Actually, they're just numbers that represent symbols. So those numbers don't have the same mathematical meaning as the math interpretation of those symbols. So if you have the symbol 1, that is like, I don't remember what it is. It's like, whatever 0 is. I don't remember what 0 is. 48 or something like that, or 60 something. I don't remember what it is. But it's not the binary encoding of 1. So this reads in those ASCII digits, the numeric value of those ASCII digits. These convert those ASCII digits to machine integers because ASCII symbol 0 has some number. If we subtract that, then ask the machine code. If we take the ASCII symbol for 0 and subtract that same value, we'll get 0. We'll get the machine code 0. And then we, in C, use C's symbols for addition to compute the addition of these two numbers and print out the result. So that's why it's an interpreter. It's taking ASCII code, which has no mathematical meaning, and evaluating the result of that program and printing it out. So that's why it's an interpreter. Interpreter gives you the output of the program. So how's that different from a compiler? What does a compiler do in contrast to an interpreter? Okay, it takes, what's that? It makes machine code, yeah, it produces machine code. And if you run that machine code, what do you get? Oh yeah, you want to say something else? Yeah.
The interpreter actually does code, interprets code and writes it. The compiler delays that, like execution until you run the program.
Yeah, the compiler doesn't need to execute the program. It doesn't need to compute the output of the program. Instead, all it really needs to do is translate it to a different language. Now, I think we talked a little in class that the boundaries between the compilers and interpreters is a little blurry. Both interpreted languages or tools for interpreting languages and tools for compiling languages do a little bit of both. But at a minimum, what the compiler does is translate to a new language. It doesn't have to do any kind of interpretation in order to achieve that translation. So the example of that code is here, where we do the same kind of processing of the ASCII characters, but instead of computing what the result of the operator would be, we instead print out assembly code. So now this should look a little more familiar because you've hopefully done the CodeGen assignments, where the kind of heart of what a compiler or code generator is literally just printing out assembly code or printing out code. Code generation is just a program that prints code. For a compiler, the goal of a compiler is to print equivalent code that's going to be the same as the input language. Now you need a specification of that input language and you need to be able to describe that they're the same, but for our purposes, I gave you an intuitive notion of what simple IR is and we translate it to assembly. But this is the key difference. Interpreter outputs the computation, what the program output should be, and a compiler translates the input program to another program. How could we get the output of this program that the compiler produces? How do we get its output? You run the assembly. Well, you have to assemble it first, make it into machine code. But yeah, who's the interpreter? What's the interpreter for machine code? What part of your system is doing the interpretation of your machine code? The CPU, the processor. The processor is a physical hardware implementation of an interpreter. So that's what the electrical engineers do, the computer architects. They design machinery, physical machinery, that are interpreters for your machine language. So that also is, if you have a desk calculator, you have some language that's inputted by buttons, and then the machine will physically compute the output for you. It's physically interpreting those symbols, those button presses, into the output. Yeah?
So we're compiling assembly x86 or whatever we're doing, and then that also has to go through a step of turning into machine code, right? Is
Yeah.
there like another step where you're saying it's just an interpretation, but on a hardware level?
Well, so I guess, sure, when you make assembly, there is more translation to machine code. But it's not compilation in the sense of translating a high-level language to a low-level language. They're kind of at the same level. It's like they're mnemonics for your machine opcodes. But once you have machine code that the processor inputs, you can think of the processor as an interpreter, as a hardware interpreter of the language. Yeah, 64-bit x86. Yeah. In the same way, your calculator, your desk calculator is an interpreter of the language specified by the buttons on your calculator, like math operations. So there's no reason you would have to, say, use this to designate the number 1. If you really wanted to, you could have different encodings for the number 1. I mean, it might be a little harder to write an adder, but you could do it. You could swap the orderings of these bits. They don't have to represent in binary. Actually, and in fact, the machines use 2's complement for negative numbers, which is not like a direct translation anymore, right? So you can use any encoding you want for the numbers. These numbers also don't have meaning until they're interpreted by the hardware. So that's why in 2's complement, the negative number won't exactly look like the positive binary version of it. So that's a case where you use a different encoding for your numbers, and it's the interpretation of those, the evaluation of them, that gives them their meaning. And plus us ascribing meaning to those symbols, and then the interpretation of those. Okay, so that's the tool chain. Any other questions on the tool chain? And actually, that was tool chain. Sorry, that wasn't tool chain. That was compilers and interpreters. We got some stuff on grammars. Okay, so here's a syntax-driven language processor. This is the grammar. What does this processor do? Does it interpret or does it compile? It's a loaded question because there's a lot of pieces to understand, but use a little, what's that? Okay, interpret. So what's the output of this? What's the data type of this value? Oh, so this is string concatenation, if that wasn't clear. So what's the output of string concatenation? A string. So the output here is a string. That string is going to have the symbol plus in it. So is this a compiler or an interpreter? Yeah. It's a compiler because it's outputting strings. It's outputting expressions. And I know that's a little tangential reasoning, a sort of indirect reasoning to see that this is. But contrast this with a interpreter where we have functions that perform the addition on the tree values.
So we can think about it as like the compiler is not actually doing the process.
Exactly. Compiler, yeah, exactly. Compiler.
When you use interpretation for somebody that doesn't speak a certain language, you're actually saying it to the other person.
Yeah, exactly. So, that's what's kind of tricky. Is in languages, the interpreter is actually a translator as well. So the interpreter really is the translator. They're also doing some interpretation by translating, they're not doing a one-to-one dictionary lexical translation. They're reinterpreting or they're rewriting it in your idiom, using your idioms. So I think that's why it's probably called an interpreter in human language. But the interpreter of language is like your head, is you, the interpreter of the language. So interpreters and translators are both, for foreign language interpreters and translators, they're converting it, they're re-saying it, restating it in a different language. to be then interpreted by you as well. But they're probably also doing, just like a compiler, the compiler is doing some interpretation of the code in order to do optimization. But that analogy kind of breaks down a little bit with interpreter. But human language interpreters and translators, they're both doing translation because they're outputting this, hopefully the same content in another human language. So in that sense, they're like a compiler or a translator. Okay. All right, so that's compiler basics, sources and source to processes, the kind of tool chain, language tool chain stuff. Let me see what else I have on here. All right, let's go to functions. Let's just go top down here. All right, stack frame. What's the stack frame? What's the use of the stack frame? Why do we have a stack frame?
So you can have scope.
Yeah, you can have scope. Yeah, you can have local variables. What else does the stack frame do? So it provides space for local variables. Why not just put them? Why not put them on the stack? Why put them in just like a single slot on the heap? Okay, parameters, communicating parameters. What else? Keeps track of the other calls to the function. So each call to the function gets its own stack frame. That allows for recursion, because if you just allocated one spot for each variable, your recursive functions would share their local variables, and you might end up with not the actual valuation of the function that you expected. So we got parameters, local variables. What else is on the stack? Well, the stack, there's a pointers to what? What pointers? Well, there is a pointer stored onto the stack to a different function. How's that stored? Yeah, how's that stored? Or were you going to say something else?
I was going to say, well, I think the fact that you can have stack variables and dynamically allocate memory for stuff as opposed to you can't dynamically compile something static. It's just going to be in one spot.
Right, yeah, so you have automatically allocated variables. That's the local variables get automatically allocated. That's right. So automatically allocated variables, parameters, and it allows each call to have its own state. So what else is on the stack? There are pointers on the stack. Pointers to what? What else gets saved onto the stack? What's that? Return address. So that's a pointer to the next code instruction to run after returning to the calling function, the caller. What else is on the stack? Yeah.
The previous base pointer.
Yeah, the previous base pointer. So a pointer to the previous stack frame. So the old RBP, the old base pointer, that's a pointer to a stack frame. And when you save it on the stack, you actually have a pointer in memory to the previous stack frame. So those are the four main things that you get on the stack. You get the return address, the old base pointer, local variables. And what about parameters? Are parameters on the stack or are they in registers? Both. They're in both, right? How many parameters are passed on with registers? 6 in the System 5 ABI, and the rest are on the stack. All right, questions on that? The ABI stuff. I think that's all the ABI stuff. Oh yeah, who's responsible? Okay, for the different parts of the stack. So we've got local variables, old base pointer, return address, parameters. Is it the caller or the callee that pushes parameters?
The caller.
Caller, because the caller has access to its local state. So the function creates the function call. The function executes the function call. To do that, it needs to push whatever local or global variables it's using. It needs to compute those values, and then it pushes them on the stack. What about return address? Who puts the return address? Caller. So the call is one instruction, and then after that call returns, we should go to the next instruction in the caller. So the caller can easily compute what that next instruction is, just program counter +1 or instruction pointer +1. Okay, what about the old base pointer? Who pushes that onto the stack? The callee does it. In the System 5 ABI, the callee does it. The caller could probably also do that, but the callee does it. The function being called pushes that onto the stack into the prologue. That's the System 5 convention. What about local variables? Caller or callee allocates the local variables of the function being called. Callee. The callee allocates those. All right, questions on System 5 ABI stuff? Okay. All right, how do we access local variables? Once in the System 5 ABI, what register holds? So first of all, what register holds a pointer to the stack frame, or is intended to hold the pointer to the stack frame? RBP. You can remember it with base pointer, if that helps at all. But base pointer is like the Intel term for the pointer to the stack frame. And how do we access local variables that have been allocated on the stack? Yeah. Go to the offset from what? From RBP. Yeah, you take RBP and do the offset from RBP. So here's an example of using an offset from RBP. Is this a load or a store assembly instruction in AT&T syntax? Who says load? Who says store? It's a store. So in the AT&T syntax, remember the destination is always the second parameter. Source is the first parameter. And that's specific to AT&T syntax. So if you go into software exploitation and you look at Intel syntax, it's swapped. Very confusing. You can sort of tell if you see a % sign before a register name, it's AT&T syntax. If there's no % sign, it's Intel syntax. Most of you probably won't have to worry about that, but if you ever do any low-level system stuff or code exploitation or disassembly, disassembly or decompilation, you may need to worry about that. Okay, yeah, so this is how we store to memory given by the address in RBP, offset by -16. Questions on that? Questions on the local variable loads and stores? Okay, let me. All right, so here's some example code that uses call and return. So this is the Intel or the x86 instruction for call. How does it change the state of the machine? So state of the machine is RAM and registers. You could also consider I/O devices or peripherals, but considering just RAM and registers, how does the state of the machine change when we use the call instruction, the machine code call instruction? So do any registers change when we do a call? Or what happens with the call? So so RBP is shifted by the prologue, so there's code that does that. It does push something, though, onto the stack. Yeah. It first pushes the return address, and that return address would be line 4, instruction 4, and then, yeah. It doesn't affect the old base pointer, so the call does not actually touch the old base pointer, the x86 architecture's call. So there's another register that you may not think of as a register that gets changed. So what's the next line of code that gets run by the machine after this call? Yeah. Yeah, on line 1. And so, yeah. The program counter gets updated. In the x86 world, it's called the instruction pointer, RIP, because if you can take control of it, then your machine is dead. So yeah, the instruction pointer gets, so first the return address gets pushed, which is basically the old instruction pointer plus 1 instruction, plus the size of this instruction. And then we have a branch. And all a branch does, hopefully if you remember from computer architecture, all a branch does is just like an add or a subtract, it modifies registers. A branch instruction just changes the instruction pointer. That's all it does. So we have push line 4 onto the stack, and then change instruction pointer to be line 1. So that's what happens on a call. What about the return instruction, the x86 return machine instruction? How does the state of the machine change? What registers or stack, either or both, change? Yeah. Branches the return address. So how does it know what the return address is? It's the first element on the stack, or it should be, as long as your function is implemented correctly and no attackers have used a stack smashing attack to overwrite the return address. But assuming everything worked correctly and the top of the stack is your return address, the return address will first pop the return address off the stack and store it into the instruction pointer or program counter. And that effectively does the branch, because the next, you can also think of it as popping it off into a register and then branching to that instruction. But it's really just popping the top of the stack off and branching to that address, changing the instruction pointer to be that address. All right, other questions on the behavior of call and return? Machine level. And so how does this call different from, say, a C or simple IR function call? How is this machine instruction call? Could I just implement a C function or a simple IR function by just translating a call to this? What's that?
No, because we also have parameters.
Yes, we have parameters. And what else do we have for C and simple IR functions that this does not do? Yeah.
Like returning things to
Return value. So return value. Oh yeah, I forgot to ask that. How in the simple System 5 ABI, x86 simplified, 64 simplified, System 5 ABI, how are return values passed between functions? RAX, the RAX register. So a return instruction in simple IR or C does not translate to this return instruction. A return translates to move to RAX, put something in RAX. What else is different about just a machine code call versus a simple IR or C function? So some of you actually said this is what the call does, even though it doesn't. There's another register that gets used for simple IR and C functions. RBP, yeah, RBP. So the call does not do anything with RBP. It just changes the instruction pointer and pushes the next instruction on the stack. Pushes the next instruction on the stack and then changes the instruction pointer. It's up to the implementer of the compiler or the writer of the assembly code to add instructions. So these are down here. So I just had it. So yeah, it's up to the assembly code writer or the compiler to add code to the callee to save that RBP. That's not done by the call instruction. Yeah.
You also add the RST to increase. In our lab the other day, we found out by looking at the compiler, whenever we had a function that didn't call any other functions, it didn't bother with updating the RST.
Oh, yeah. Interesting.
I guess that makes sense because it's not being like you said all then it doesn't really matter. But as soon as we added another function called function, even when it didn't do anything, then it updated the RST.
You mean this one? Did it set RBP though?
Yeah,
It set RBP, but didn't even bother.
Yeah.
Yeah, I think there's something on that like x86 page that there's for like leaf functions.
Yeah, for these functions, I guess makes sense because then updating RC doesn't really affect anything for these functions.
Yeah, I think that's right. There's some like
Pushing anything to the stack.
yeah, there's this like red zone that like I think the machine is supposed to, or your code is supposed to like preserve, and I think that's what they said for leaf functions. Yeah, leaf functions can be used for their stack frame. Yeah, that's this. And this is specific to the AMD 64. AMD actually created the x86 64 instruction set because they beat Intel to the punch. So I shouldn't say Intel x86. It's really AMD's 64, but you can say x86 64. But this is specific to the AMD 64 ABI. I don't know if 32-bit or ARM uses this as either. But just like with the registers used in parameter passing, this is like focused on better optimization, I guess, like allowing the compiler to do more optimization. Oh yeah, it says right here, it's an optimization. But for our purposes, we have to worry about optimization. Just remember that RBP is updated, is not updated by the machine code call and return. That's code that's inserted by the compiler. That's code that's inserted by the compiler in order to emulate C and simple IR functions. The machine itself does not have inbuilt support for local variables or recursion. Instead, it provides a register that you can use by convention. You don't actually even have to use that register, that you can use by convention to emulate C or simple IR style functions with local variables and support for recursion. And you'll see this kind of stuff a lot in systems and machines, where you have simpler languages, simple machines, and you can emulate any other machine that is equivalently powerful in that. So if you ever play with video game emulators or hardware emulation, it's using the same principle, using the same principles here, language principles. Yeah? Oh, okay, that's a good question. So it's a little off topic, but if you're doing this in C, if you want to have template-like or generic-like stuff, programmers often use the preprocessor to simulate this. C++, its templates are actually a preprocessing step. They operate very much like a C preprocessor. So if you're a C++ programmer, you ever wondered why you need to put your implementation of template code in a header file? That's because it's actually kind of preprocessed. Higher level languages or languages with more support for generics will do this in the compiler stage, and sometimes even in the runtime stage. So Java, for instance, will store type information about generics in memory with the type. They'll also use some optimization at compile time to remove those if they know what types they're going to be. But this is more of an advanced topic, generics and templates. And just as another little add, so compiler construction is now on the schedule. It took a little while to get it rescheduled. I moved it to fall. So it's going to be fall, Monday, Wednesday at 3. So if you're interested in taking compiler construction, you want to learn more about how more of these sort of advanced language features are created. There's now a compiler construction course, fall, Monday, Wednesday at 3. So this fall it'll be Monday, Wednesday at 3. But yeah, that's a good question. But it sort of depends on the language implementer. It could be pre-processing, could be compilation, and it could be done at runtime. It could be the compiler inserts extra code so that at runtime types are managed. And all three are used, sometimes even in the same language, in various combinations, depending on the language implementation. And different language design constructs are easier or harder or impossible or not impossible to do at compile time or pre-processing time. But yeah, advanced stuff. Take compiler construction if you're interested. All right, other questions on functions, how they're implemented, compiler basics, language tool chains. Okay, let me make sure I've covered all the questions for the second half. That's the register. All right, so yeah, make sure you're solid on how the RBP is used. Into the symbol table, I have several like open-ended questions where you write assembly code. So make sure you're able to write assembly code where you can use that pattern of using offsets from RBP. All right, let's do arithmetic. So what simple IR instruction might this correspond to, or at least in part correspond to? Yeah, a plus sign, yeah, so it's a plus sign. So yeah, just be aware. I mean, they're pretty straightforward for add, subtract, and multiply. I'm not going to ask you about division at all. I'm not going to ask about division because it's such a pain. I don't want to have to remember it either. I use a reference to look it up, and it's sort of just got to be a bunch of extra space on your sheet. So I'm not going to ask you about x86 division. It's just so annoying. But addition, subtraction, multiplication, they're pretty straightforward. So if let's look at subtraction. So let's say RBX has 3 in it and RAX has 2 in it. What's the result of this subtraction? So RBX is 3, RAX is 2. Yeah. What's that? The value get put into RAX is, who says 1? What's that? Yeah, RBX has 3 and RAX has 2. So it's not 1, surprisingly. What is it? It's -1. So this is just to illustrate the confusing part about assembly, AT&T syntax for assembly. This is both the destination and the left operand. I know that's super confusing, but this is the AT&T syntax x86 64 assembly mnemonic. This is the kind of semantics of it in a more readable math notation. So it's RAX is the left operand, RBX is the right operand. And so if you replace this with subtraction, you'd have 3 here, 2 here, and it'd be -1. So I'm not going to like quiz you on this like in detail, but just so you remember to write some like a correct assembly code. Yeah.
Would a good way of understanding it be like kind of like the minus equals operator in C, or like the plus equals operator?
For this like update part, yeah, you can think of it like minus equals or plus equals for sure. The tricky part is that this is the left-hand side. That's the annoying part of AT&T syntax. But yes, this is just, it is like that. And actually you could translate it into that, right? It's like minus equals or plus equals in C or other languages. It is exactly like that in the x86 world. All right, so that's subtraction, and then multiplication is similar. It's the same idea. I'm not going to even test you on division. Division is just a pain. All right, so just remember the kind of simple compilations of the simple IR languages, the compilation of simple IR languages. So here's how you can translate all of the additions, subtractions, and multiplications. They all can be translated using the same pattern. So you just load, so if this is, what am I loading here? A and B. So x equals A plus B here. X equals A plus B. You load the 2 parameters. So this is how you do a load from memory using an offset from RBP. Same for a different offset, given this table here. So I'll give you the table whenever you need to know offsets. I'll just give you the table. This is how you do the loads from memory into a register. You can't do multiple loads or stores in the same assembly operation, just like in MIPS. MIPS just has separate load and store operations. You can't even combine it with addition. Intel you can, or x86 you can. So we load these 2 into registers, and then we perform the add, subtract, or multiply on them, and then store the result. That's how you translate an arithmetic operation.
You're saying the assembly code in the test will be based on the addition and subtraction, or did you say it was on the division?
I'm just saying I won't show a division or modulo, but there'll be branches, arithmetic, and pointers. Pointers will be the trickiest one for sure. But you have the patterns, you have the code patterns for all 3 of those instructions. And it's simple IR, it's not a complete, like a C expression. All right, questions on arithmetic operations? This is the pattern for all 3 that will be on the test. I'm not going to ask the division one because it's just kind of a pain. Okay. All right, let's do branching. So unconditional branches are super simple. They look almost identical to simple IR. So that's jump in the x86 world, called jump instead of go to or branch. Labels are written the same way, so hopefully that's no surprise. Okay, so for instance, this. How would we implement this in x86 assembly? This, simple IR semantics.
We're going to get like reverse, basically.
Okay, so you got to reverse the operands to what instruction do you pass? So sure, yeah, same problem where you have to reverse the operands. Yeah. Okay. That's right. That's right. So we have a compare. So to do that single simple IR instruction, which is a conditional branch, in the x86 world, you use two instructions. You first do a compare, and then do a branch or a jump for whatever comparison you'd like to do. There are different jump instructions for each type of comparison. Yeah. What's that? You still need to reverse these operands on the compare. On the compare, yeah, not the JLE. For the compare, you do. Compare is basically a subtraction where it doesn't update the result. So it works the same way as subtraction. So if you reverse them, it would be like less than, greater than would be less than would be greater than. But I'm not going to be too nitpicky on that stuff. Yeah.
You're saying, well, the compare doesn't like return anything, but it's like
what it does is there's a special register called the E flags register in the architecture, if you remember, and it's not something you can directly observe, I don't think, from the instruction set level, but it gets set. It's like a hidden register that gets set behind the scenes, and it affects the operation of other instructions. So like the branch instruction, this branch instruction will inspect that register. So you can think of like this as having an output, like you said, where the output is either there's two outputs that matter, which is 0 or is less than. And knowing those two, you can
specifically go from like the compare to be like if this was true or if this was not true.
No. There's no notion of a Boolean operation here. There's only like, was it 0? And so that's why in C, 0 is used for false because you just compare to 0 and then it's false. And anything else is not false. So the way you check whether something is true is you just check if it's false and then don't jump, or jump if that's whatever the semantics you were trying to implement. But that's why in C you can just put anything in the condition, and if it's not, as long as it's not 0, that condition is true. So it works here by just comparing to 0. And if the comparison's not true, then, or the comparison is not 0, then it's true. So again, that's stuff again more for graduate compilers to see how that compilation works. It's just a little Boolean math, Boolean logic. Okay. So here's this table of the different x86 assembly operations for each of the simple IR operations. So that makes it pretty straightforward to implement simple IR branches. You always do a comparison, and then you just pick the corresponding jump mnemonic. And just like with arithmetic, at least how I implemented the compiler, the simple template way to do it was just always use RAX and RBX, and then that makes the template really simple, in my opinion. Questions on branching? Okay. Let's go over the most fun one, pointers. Let's see. All right, what does this assembly instruction do? What's the resulting change to the state of the machine? Yeah.
It treats RS as an address and goes to that address and gets the value inside the idea.
Yeah, that's right. So this is, like in the MIPS world, this is a load, even though it's using a register. The parentheses in the AT&T syntax world denotes basically pointer dereference. It's meaning do a load, but use the value of RAX as the address to load from. So this is the kind of confusing part about, or the sort of easy part about the x86 world, probably for writers of assembly, but the kind of annoying part for looking at assembly is that some move instructions are register copies, some are loads, some are stores. So this is actually a load from memory. But the memory address is not hard-coded. Instead, it's an address, whatever the address in RAX is. So that's the meaning of this. And you saw this with variables anyway. So variables do the same thing, where we have RBP, and the syntax and the machine actually supports putting an offset. In the AT&T syntax, you put the offset before the parentheses. Maybe confusingly, you put the address there, but it's basically like an array index. You put the offset here, and it'll look up RAX plus whatever that offset is to find the address to load from. Okay, so that's okay. So what simple IR pointer operations? There's three: reference, dereference, dereference, assign. Which of those use this addressing mode, this register indirect load? So there's three of those. Reference, one gets the reference of a variable, or the address of it. One loads from a dereferenced address. One stores to a dereferenced address. So which of those uses this addressing mode? Is it none of them, all of them, one of them, two of them? Yeah. Yeah, dereference and assign. So why doesn't reference use this addressing mode? What do you have to do for reference in order to get the address of a variable? Or how do you get the address of a variable? So can I do like -16 RBP?
You have to go to the offset first, and then you get the address. Like you shift to the offset, and then the offset address. Kind of you put it.
Okay, let's go through it. So to get the reference, so remember what we're doing. We have to get getting the reference. Let me get the board for this. So keep in mind what's happening when we get the reference. So T1 is getting the address of X. So T1 equals &X. So we've got the addresses in memory, and then we have the memory values, the values at those addresses. So when we get the address of X, we're not getting its value 8, we're getting its address 88 and storing it into T1. The problem is we don't have fixed addresses at compile time. We don't know what address, in general, that X will be located in memory. But we do know it has a fixed offset from whatever RBP is, because we generated our code so that RBP would always point to the stack frame. We can generate code that will compute at runtime the address of X. And we can do that using RBP. So we write code, we generate code that will take RBP and add whatever the offset is. Because at compile time, we know RBP. We know where RBP is. We know its name. We know it will always contain the address of the stack frame. And we know the offset. We know that at compile time. So at those two pieces of information, we can generate code, we can generate assembly that will compute this offset 88, or compute this address 88. And here's what that looked like. So this is what it looked like. We took the stack frame address, which we know at compile time will be in RBP, and we copied it to RAX, so we don't overwrite it. And we know the offset of the variable X. We know that at compile time, so we can generate code that will add that offset -24 to RAX. So now this guarantees, these two steps guarantee for us that at runtime, RAX will have the address of X. Because we as the compiler writer designed this output code so that RBP would be the address of the base pointer, and that -24 would be the offset of X. Because that's whenever we see X, we translate it into a load or a store from offset -24. So knowing these two pieces of information, we can generate code that will compute the result for us, the value, the address for us at runtime. It's kind of the cleverness of compilation and the cleverness of translation between languages. In the same way that you can solve an algebraic expression, you have x squared plus y equals something or other, you can compute without knowing the values of x and y. You can figure out what x will be, or you can create a new expression that will make x easier to compute. So it's the same thing here, where we know RBAP at -24, and we can generate code that will compute the address, and that will compute the address at runtime, not at compile time. And then once we have that, we can use the same store in order to save it to our variable that we're assigning to. So that's this simple IR, T1 equals ampersand x, the address of x. This is the compilation of it. Questions on this? Okay, so then the other two pointer operations, these are using this register indirect, or whatever it's called. I don't even know if that's the real name, but register indirect move, where we're using the address in a register to load or store from memory or to memory. Okay, so for both, and the pointer dereference and dereference assign are fairly similar. They look just like an assignment. So what does an assignment do? An assignment loads from one memory address and stores to another. So if we have like x equals y, we load from the address associated with y, the offset from RBP, and store to the address associated with x. For a dereference, when we load the value from the right-hand side, if this is, for instance, this, where we're loading from the dereference of T1, we first get the value of T1. The value of T1 is going to be the address we want to dereference. And that's no different than getting the value of an integer or any other value. Remember, the RAM or the machine itself or the RAM does not care what data type you have. It's all just bits to the machine. It's when you use an operation on those values that imposes some data type, that imposes some meaning of the data. So we just load whatever the value of T1 is, and then we use this register indirect load to dereference that value. So RAX holds the value of T1, which is presumably an address, and then we load from that address using this indirect addressing mode into RBP. Once we have the value of the dereference pointer, then we can store it into the left-hand side, the T2. Questions on that? So dereference load, or just dereference. I called it simple IR. All right, and then dereference assign is sort of similar. At least it uses this register indirect move again, except instead we're using it as a store. We're storing to whatever address is given by RAX. So if we've got, say, this, where we're trying to store 11 into the dereferenced pointer T1, then same thing, we take the value of T1, we take the value of the right-hand side, and then instead of loading from the dereference pointer, we store to the dereferenced pointer. Questions on this? I guess we did this recently, so maybe it's fresh in your mind. Questions on any of this content, second half content? I'm not going to ask any questions about stack smashing. That was just for fun. Any questions on the second half material? Okay, let me quickly go over the first half, since there'll be stuff on the first half. Let me look at the actual questions. So remember, they're all going to be multiple choice. I'm not going to make you write code, like C code or anything, for the syscall stuff. Just know the syscalls. All right. How do you save a file in Emacs? Forcing everyone to learn Emacs, yeah. Control X, Control S. How do you quit Emacs? Control X, Control C. Okay. All right, cool. Yeah.
Is that like a word answer?
These are all going to be multiple choice. Is there a Vim alternative? Sorry, no. Use Vim on your own. Vim is great. Use it on your own. It was a little rough when people picked it last semester. I had it as an option, and people picked it, and the whole mode setup was I think unfamiliar to many people. And I'm probably going to weaken the editor requirement next semester as well, because I don't think people liked it very much. But at least you can edit stuff on the command line now, I hope. What's that? It's not that bad. It's not that bad. And if you use, pausing and resuming processes, it makes it much easier.
That's when I'm gonna have a problem.
Oh,
Yeah, after you notice forget.
you just forget it, yeah. I have a coffee mug with Emacs instructions on it. All right, so that's the editor. All right, Git. I'm going to ask some more stuff about Git because you really, really should all understand Git and version control. You will, if you're going to be a software engineer, or really in anything technical or anything in computing, you'll be using version control for sure. So what Git command copies from the local repository to the remote repository? Push. All right, so there's 4 pieces in Git, and other version control is similar, even if it's not as fine-grained like the operations you have. You have your working directory, which is where you write your code. That's where you have your modified versions of your code. You have your staging area, and this is a little unique to Git. That's where you collect changes together. So that way you don't have to commit everything in your working tree. You can be working on multiple features at the same time. That's your staging area, and then you have your local repository. That's where you actually log your changes, and then remote repository, or many remote repositories, that's where you synchronize your log of changes. So local is after you've already committed your changes. That's stored in the local repository database. Push and pull, move contents, move changes between different repositories. So yeah, I sort of gave you one of the more sort of complicated version control systems. It's decentralized. It has the staging area. It allows really fine-grained control. But if you can use that, it's like a manual transmission. If you can drive manual, you'll have no problem with automatic. If you drive automatic without manual, maybe you won't understand how to save fuel or drive on snow or stuff like that. So learning the kind of manual first, I think, is easier to go to the automatic, and then you'll understand when things go wrong. Okay, remote to local. I think I just said it. How do you get change? Pull. Yeah, pull. What command stages a new file? What command stages changes? Add stages changes. And then what command creates a log of a change to the staged file to the local repository? Commit. That's a fancy way of saying commit. So working directory, add to the staging area, commit to the local repository, push or pull to and from other repositories. Let me make sure I caught all of that. Yeah, I think I got all the Git stuff. All right, navigation. What's the working directory in Unix-like systems? How do you view the working directory? PWD, print working directory. What's the syscall for? I didn't ask you the syscall for it, but how do you change the current working directory? CD and bash. How do you do it in a C program? What's the API call? It's chdir, change dir. So that's the API call for it. So that's what so when you run CD in the bash interpreter, that will call chdir. That'll call change directory at the API. Yeah.
That means you open a file, by default it's always adjacent, like the same directory as the exe, but if you were to do that change, or
exactly, yeah. Yeah, that's why, so what your colleague's asking is, that's why when you run a program from bash, like say you run your own C program and you call open, it's got to be relative to your working directory when you use the open command in bash. So when you change your working directory, if you call chdr, it's going to change the working directory. And Windows has this concept as well, I think. Yeah. Yeah, I'll ask the difference between those two. Directories. How does what like technical feature? Sorry, go ahead.
So for the whole CH so that's just for the program execution once it's over.
That's right. Yeah. So each process, the kernel, the operating system maintains the working directory for each running process. So it's tied to each process. So bash, remember bash, you wrote mysh. Bash is just a program that runs on the machine, and it has its own working directory associated with it by the kernel, by the operating system. And yeah, so it issues change dir commands on your behalf when you type cd. Okay, what technical feature of the Unix file system allows it to have a hierarchical file system? Or what is a hierarchical file system? What's that? A tree. You have a tree structure, so you have directories, and those directories can contain files. On kind of old, very old DOS, you only had like one level directories. You couldn't have nested directories. What feature or what technical aspect of the way Unix implements its file system allows for nesting? Yeah.
Directories of files and directories list files.
Yeah, exactly right. So directories are files. They're just another type of file. But instead of containing, or the semantics of them, so they're like other files, they're just bytes. But the file system treats it as a listing of its contents, of its own content. So a directory file is just a listing, like a phone book, mapping name to inode number, mapping name to the actual file data, or the pointer to the file data. And because directories are just files, they can be stored inside other directories, just like other files. They can be listed in other directories listings. And that's what allows the Unix file system to be hierarchical, is that directories are files. Directories can point to other files, so they can point to other directories as well, and you can get this tree-like structure. Now on disk, it's really just a file. That's why if you look at the size of your directory, and you look at a directory, a subdirectory, it's going to be like 64K or something. It's going to be something small. So you look at directory file, so here's my functions directory. It's only 4K, but inside, well, it might be larger than that. I don't know if it's larger than that. So inside it's 68K. So how is it possible that the function directory can be 4K when the contents of it are 68K? That's because this is the size of the directory file itself, of the listing, the directory listing. And this tool, well, if you want another little tool, du, disk usage, this will show you like actual contents, the size of all contents. Or on Mac, you can say like, compute directory sizes for me. Yeah.
Like, I guess in Mac, the directory is the number of names inside the directory. It's the story behind the names, I guess.
Yeah, that's kind of right. Yeah, so if you take the size of the phone book, that's not the size of the people or something, right? Like the weight of the phone book is not the weight of all the people in the phone book. Yeah, that's a good way of thinking of it. Yeah, yeah. So it's just it's proportional to the number of files. This 4K is proportional to the number of files in there, not the size of those files. If that makes sense. Okay, files. Oh yeah, so syscalls. What are the syscalls that are used for files? I think we went over like 3 or 4 of them. Just call them out. Open, close, what's that? Write, read, and then CHDR. I guess I think that's all we had. So open, close, read, write. What about for processes? What calls do we use there? Fork, exec. Exec VP and all the variations of exec. Yeah, there's a whole bunch of variations of exec. We had pipe as well. I'm not going to ask about pipe. Yeah.
Should we be looking at each variant of exec as well?
You don't have to look in the variants. I didn't even show you the variants. I should. Yeah. Dupe. Yeah, that's right. So we had dupe and pipe. I'm not going to ask you about those. I'm not going to ask you about dupe and pipe. Let me make sure. I'm not going to ask you about those. Yeah, I'm not going to ask you about dupe or pipe. Actually, no. Pipe is on here. So what does pipe do?
Connects the output to the program.
Dupe does that. Pipe just creates the file. So you won't actually have to know what pipe does. If you kind of listen to what I'm saying legalistically, you don't have to know what pipe does. But it will be mentioned, if that makes sense.
Could you repeat one more time?
So just know the syscalls for processes,
Like the process.
fork and exec, and the word pipe may appear on the exam, but you don't actually have to know what pipe and do bar. I'm not going to actually make you know what pipe and do bar. So if you just know fork and exec. All right, so difference between fork and exec. What does fork do? Duplicates the process, makes a new process. It does not replace, it does not like run a new program. It's the same program. What does exec do? Changes what program is being running. Does exec create a new process? No. Exec doesn't create a new process. If you want to create a new running program, fork, then exec. If you just run exec, you have the same process, you replace the program. If you just run fork, you have 2 copies of the exact same program running, except the return value of fork is different. All right, that's 1020. All right, everyone. See you on Wednesday.